Hello, my name is Aaron Kindred, and I'm currently a junior pursuing a bachelor's degree in physics at Tennessee Tech University and worked under Dr. Rajabali for this project. Today I will be discussing what NEXT is and how it will impact future research involving neutron detection. The goal of this summer project was to document the scattering patterns for monoenergetic neutrons and gamma rays at different increments of energy. NEXT will not only improve our current knowledge of nuclear physics, but also provides a new perspective on the decay patterns of neutron unbound states and nuclei. NEXT is a combination of 4x8 segmented inorganic scintillators seen in Figure 3 with 8x8 photomultipliers on either end of those. Now, in comparison to other neutron detectors, NEXT uses pulse shape discrimination to differentiate between gamma rays and neutrons, all while maintaining an energy resolution factor of at least 5. NEXT also utilizes its many segments for position tracking capabilities seen in Figures 2 and 4, which is what I'll be discussing more in depth later on. NEXT is continuously being simulated with the JMOT 4-based software NEXTSIM, while the collaboration anxiously awaits experimental results from its first functional model. My role in the NEXT project consisted of running NEXTSIM and making sure that the results produced were reasonable to what was expected. A NEXTSIM simulation reads from an input file in which the user will define the simulation space, general properties of the detectors and source, and the number of primary particles from the specified source. All interactions encountered by the primary particle within the simulation space are recorded, and previously specified data such as energy or center of mass from the interaction is stored in the resulting root file. Eventually, the primary particles will either leave the simulation space or be completely absorbed by objects or processes within the space, ultimately rendering a complete entry for that primary particle and moving on to the next one. I constructed a macro to use in a root environment which fills various histograms, some of which are shown here in Figures 4, 5, and 6, and calculates scattering statistics for primary particles. For each simulation, I set the number of primary particles to 100,000 and incremented the energies of the particles by 1 MeV, all the way to 10 MeV for neutrons and 6 MeV for gamma rays. After some time debugging my code, I'm now able to produce consistent spectra and print out scatter statistics to the root environment. The most notable spectra are shown here in my poster. Figures 5 and 6 show the difference in segment between the first and second scattering of a 1 MeV primary particle for gamma rays and neutrons respectively. Figure 2 is an experimentally gathered position plot using a cobalt-60 source, and in comparison to Figure 4, a simulated position plot, can arguably vouch for the effectiveness of NEXTSIM and my macro. Finally, I would like to discuss the results of my research. Let me remind you that the goal of this project was to document the scattering patterns for monoenergetic neutrons and gamma rays at different increments of energy. In regards to this goal, we found that neutrons showed a 7% increase to a 66% maximum and forward scattering at 8 MeV while approaching maximum energy. Gamma rays showed an increase of 8.6% and a maximum of 57.6% forward scattering at 5 MeV. Both neutrons and gamma rays are less likely to interact at higher energies. Neutrons decreased from 100,000 to a total of 36,000 interacting particles at 10 MeV, with only 10,451 scattering more than once. Gammas above 6 MeV have even lower statistics, with 12,900 total interacting particles out of 100,000, and only 2,853 scattering more than once. To conclude, I believe the more erratic behaviors observed towards the higher energy range of each particle are partly due to the lack of statistics that are comparable to the low energy counterparts. Otherwise, a generally direct linear behavior of increased energy to more forward scattering can be observed. I look forward to speaking with you and answering any questions you may have. Thanks to the NSF for funding this project, and thank you all for listening in.